We learned in section 7 about the damage, the miners rule, and how to plot the accumulative damage. Now we will put that into application and see how the accumulative damage is a very important tool to determine the useful life of the structure and to take very important decision that has big economic consequences regarding replacing or repairing or refurbishment of your asset. Here we are going to use a real life example to explain how we can use Miner's rule to calculate the remaining useful life of a structure based on the Euro code and Australian code. We will go for a pedestrian bridge. Our example is an existing pedestrian bridge over a rail corridor that meant to be designed for 100 years service life. The age of the structure is 35 years. This bridge configuration gives us wind exposure area of area 1, which enables us to calculate the wind pressures and the wind forces, and from there we can get the wind stresses to use it for fatigue check. As we learned before, we are able to plot the accumulative damage curve for 100 years service life for this configuration based on the calculated wind-induced stresses, and we can obtain from this curve two things. First is the total damage, okay, and second is the incremental damage, which is damage per year, and it equals to the total damage divided by the service life, which is 100 years. Okay, all right, and from there, as long as we get the incremental damage, the damage per year, we should be able to calculate the damage at 35 years age, which is the age of the structure multiplied by the damage per year. 35 years multiplied by the damage per year, or the incremental damage per year. And this is sort of showing that the damage, the accumulative damage using the incremental damage could be related to the age of the structure. So we could know how much damage happened at the age of 10, at the age of 20, at the age of 30 years, and so on, all the way to the service life of the structure. Now we have two lives to the structures. We have the fatigue life and we have the service life. Fatigue life basically is the service life divided by the total accumulative damage. Okay, the service life divided by the total accumulative damage. If your damage is less than 1, as here in the example, let's say that your damage is 0.8, for example, so your fatigue life is more than 100 years because it equals to the service life divided by the total damage. 100 years divided by 0.8 gives you 125 years. For you as a designer, you stick to the minimum of the fatigue life or the service life. And in our case, the service life is the minimum, which is the 100 years. Meaning that the remaining useful life for our existing bridge is the 100 years, which, as I said, the minimum of the fatigue life or the service life, minus the age of the structure. So 100 years minus 35 years gives you 65 years remaining surface life. So this bridge should be all right and functional, and there is no harm or potential fatigue failure for another 65 years. If your damage is more than 1, the total accumulative damage is more than 1, let's say 1.25. In that case, fatigue life equals to the design service life, 100 years, divided by the total accumulative damage, which is 1.25. In that case, it gives you 80 years. From there, we can see that the minimum of the fatigue life and the service life, in our case here, is the fatigue life, 80 years. So again, the remaining useful life is the 80 years because it's the minimum, minus the age of the structure, 35 years. So the remaining useful life is 45 years. That means that this structure, we should not expect failure due to fatigue for another 45 years. And this structure is unable to serve the full service life, which is 100 years. It's only able to serve 80 years. Okay, this is another real life example to calculate the remaining useful life based on Eurocode using Miner's rule. So we have our accumulative damage curve for 100 years design service life, and we're going to use the same example that we used in the previous slide, which is an existing pedestrian bridge over a rail corridor with a wind exposure area 1 with the same age, 35 years, and with the same design service life, 100 years. We can plot the damage curve for this configuration X, as we can see here in the blue curve. And then the client asked us to add a safety screen at the age of 35 years, which changed the configuration of the breach from configuration X to configuration Y, and changed the wind exposure area from area 1 only to area 1 plus area 2. Again, we can plot the cumulative damage curve for configuration Y as shown here in the green curve, knowing that this green curve, the cumulative damage curve, is a plot of the damage for configuration Y, as if the bridge has been built with this configuration from day 0. Now, the same data we used in the previous slide regarding the service lives, the service life 100 years, the age 35 years, okay? So if we have a wind exposure area 1 plus area 2, we can get the wind pressures and calculate the corresponding wind-induced stresses based on configuration Y. And we can see here that there is excess damage from configuration X damage curve to configuration Y damage curve. This is excess damage, obviously, because the wind exposure area has increased. Now, we're still able to calculate the total damage for configuration Y and the total damage from configuration X. That's straightforward, as we learned before, but the tricky part is the incremental damage per year, okay? So if getting the total damage for configuration Y is straightforward, getting the total damage for configuration X is straightforward, the incremental damage per year is a bit tricky because we have two incremental damage per year. One is before adding the safety screen. So we have an incremental damage per year before the age of 35 when the safety screen has been added. And then we have another incremental damage per year after the age of 35 years when the safety screen has been added. Okay, so to calculate this, first we calculate the damage before adding the safety screen. And before adding the safety screen, the bridge configuration follows configuration X. So the incremental damage per year should be total damage for configuration X following the blue curve divided by the intended design service life, which is 100 years, which is similar to what we've done in the previous slide. So damage per year before adding safety screen at age 35 equals to the total damage for configuration X coming from the blue curve divided by the intended design service life 100 years. Now we come to the damage per year after adding the safety screen. So the theoretical remaining life of the structure that the structure is intended to serve is 65 years, which is the intended design service life 100 years minus the age of the structure 35 years give you theoretical remaining service life 65 years. So the expected lifespan for the structure after the age of 35 years is 65 years. That doesn't mean that the remaining useful life is 65 years. It might be less than 65 years, it might be more than 65 years. It depends on the total damage calculated for configuration Y after adding the safety screen. So going back to the incremental damage per year after adding the safety screen, as we calculated the remaining theoretical life 65 years, we have to calculate the remaining accumulative damage. So the damage started to accumulate based on configuration Y between age of 35 and the intended design service life, which is 100 years. So the remaining accumulative damage should be the total damage for configuration Y coming from the green curve minus the damage accumulated at the age of 35 years, which is the age of the structure. Getting the damage at the age of 35 years should be similar to what we've learned in the previous slide, which is the incremental damage before adding the safety screen based on configuration X, incremental damage per year, multiplied by 35 years. That gives you the damage accumulated at the age of 35 years. The remaining accumulative damage will be the difference between the total damage, accumulative damage, based on configuration X coming from the green curve, minus the accumulated damage at the age of 35 years based on configuration X. That difference divided by the theoretical remaining life, which is 65 years, gives you the incremental damage per year after adding the safety screen. All right, once we reach to that point, we want to understand or we want to explain or demonstrate a fact. The fact that neither the blue curve nor the green curve represents the actual accumulation of damage for configuration Y, because it doesn't reflect the history of this configuration. This configuration came to being at the age of 35 years. Before 35 years, the bridge followed configuration X. So the actual damage curve for configuration Y shouldn't be the green curve, because as we said in the beginning, green curve is the cumulative damage for configuration Y as if this configuration existed at day 0 of the age of the structure. But the actual cumulative damage curve for configuration Y, taking into consideration the history of change in the structural configuration, should be a mix of the blue curve and the green curve, and that mix shown in the red curve here. So the bridge with its current configuration with the added safety screen at the age of 35. Before adding the safety screen, the accumulation of damage followed the manner of the blue curve. Once the safety screen is added, we had an excess in damage that started to build up as the structure is aging, causing damage hike, bringing the behavior or getting the behavior to jump from the blue curve of configuration X to follow the manner of the green curve of configuration Y. So the red curve represents the actual accumulation of damage of configuration Y because it takes into consideration the history that reflects the change in the bridge configuration from X to Y without safety screen, with safety screen at the age of 35. And this history is reflected in the damage hike shown here happened at the age of 35 due to the increase of the wind exposure, meaning that this bit of the blue curve should be considered as a virtual future because it's not going to happen. Configuration X has gone at the age of 35 once we added the safety screen. And this bit of the green curve is a virtual history because it didn't happen. Configuration Y did not exist before 35 years. So hence, the final accumulative damage curve for configuration Y that takes into consideration the history of change in the structural configuration should be the red curve shown here. Again, we will have to calculate the fatigue life, which is simply the intended design service life, 100 years, divided by the total damage of the final configuration of the existing bridge. The final configuration Y now is configuration Y. So the fatigue life will equal to the 100 years design service life divided by the total damage of configuration Y, not configuration X. And from there, again, we have the two scenarios that we spoke about in the last slide, which will give us the fatigue life, and we should compare that to the service life. Whichever is a smaller value, we stick to that value to be the useful, to be the actual life that the structure should be able to serve without any significant deterioration in the behavior or in the reliability of the performance. The last example here is for the American code using H2 because I said it's very important to understand how H2 works. You're gonna use it for checking the sign support structures and traffic structures and so on. So in this example, we're gonna use the same bridge, the same pedestrian bridge with the same configuration over a rail corridor, the same service life, the same age, Okay, and we're gonna go through the H2's load model to calculate which one is the critical to get the stress range required to check the fatigue. And then actually H2 gives you for the existing structure, as we said, H2 follows the finite life approach. And from there you go in the tabulated in the tables of H2 to get finite life constant, which is A, called A. This equation enables you to calculate the number of cycles of wind load induced stress cycle expected during the lifetime of the structure, which is quite straightforward and easy. It's easier than the Miner's rule, but the tricky bit comes here. H2 says that when assessing the finite life of an existing structure, the number of wind load induced stress cycles expected during the lifetime of the structure should be estimated. That's the point. So these number of cycles that you obtained here should be estimated from analysis based on historical wind records or directly by field measurements on similar structures as decided by the owner. So basically, you go through the calculations. H2 gives you the number of cycles expected during the lifetime, and then you go through field measurements or historical wind records and check what is the actual number of cycles expected during the lifetime of the structure. If you did this exercise in the blue cloud here and you find out that the number of cycles by field measurements or historical data is less than the number of cycles allowed by H2, so you should be okay. But if you found them more than the number of cycles allowed by H2, so you are in trouble. Not in trouble, but the remaining service life will be less than what is given in the equation. Okay, and that's about it. You cannot go any further from the historical wind records. You should be able to understand how many cycles will occur over how many years. Comparing that to the number of cycles estimated by H2, that gives you what is the remaining useful life of the structure.